The universe operates according to principles that often defy our everyday intuition. Among these fascinating phenomena is time dilation, a cornerstone concept of Einstein's theories of relativity that reveals how time itself can flow at different rates depending on an observer's frame of reference. In the vast cosmic laboratory of astronomy, time dilation manifests in spectacular ways, affecting everything from distant quasars to the practical operation of GPS satellites. Recent astronomical observations have provided compelling evidence of time dilation in the early universe, confirming Einstein's predictions and deepening our understanding of cosmic evolution. This report examines the theoretical foundations, observational evidence, and implications of time dilation in the astronomical context, illuminating how this remarkable effect shapes our perception of the cosmos. Time dilation emerges directly from Albert Einstein's theories of relativity, which revolutionized our understanding of space, time, and gravity. In 1905, Einstein published his special theory of relativity, introducing the radical concept that time is not absolute, but relative to the observer's frame of reference. This marked a profound break from the Newtonian view of time as flowing uniformly throughout the universe. Special relativity predicts that a clock in motion relative to an observer will appear to tick more slowly than a stationary clock, a phenomenon known as velocity-based time dilation. The mathematical expression for this effect involves the Lorentz factor, 1 v2c2, where v represents the relative velocity and c is the speed of light. As an object's velocity approaches the speed of light, this time dilation effect becomes increasingly pronounced. In 1915, Einstein expanded his framework with the general theory of relativity, which describes gravity as a curvature of space-time caused by mass and energy. This theory introduced gravitational time dilation, whereby time passes more slowly in stronger gravitational fields. Specifically, a clock situated near a massive object in a deeper gravitational potential well will tick more slowly than an identical clock positioned farther away. Both forms of time dilation, velocity-based and gravitational, have been repeatedly confirmed through precise experiments and observations, establishing them as fundamental aspects of our universe's operation. The concept of time dilation did not emerge solely from Einstein. Several scientists at the turn of the 20th century contributed to its development. Joseph Larmor in 1897 and Emil Cohn in 1904 formulated equations describing time differences for moving objects, particularly for electrons orbiting a nucleus. However, Einstein was the first to recognize that this effect pertains to the fundamental nature of time itself, and to emphasize its reciprocal or symmetrical character. The concept was further refined in 1907, when Hermann Minkowski introduced the notion of proper time, providing greater mathematical and conceptual clarity to time dilation. These theoretical developments laid the groundwork for understanding how time dilation manifests in astronomical settings across the vast expanses of space. In the context of astronomy, velocity-based time dilation occurs whenever there is relative motion between an observer and an astronomical object. According to special relativity, if two observers are moving relative to each other, each will perceive the other's clock as running slower than their own, a seemingly paradoxical but experimentally verified phenomenon. For objects moving at a significant fraction of the speed of light, such as particles in cosmic rays or matter falling into black holes, this effect becomes substantial. The formula indicates that as an object's velocity approaches the speed of light, the time dilation factor increases dramatically, approaching infinity as v approaches c. This means that from an Earth-based observer's perspective, processes occurring in high-velocity astronomical objects appear significantly slowed. Gravitational time dilation is equally significant in astronomy, as it affects any process occurring in varying gravitational fields. Near massive objects like neutron stars or black holes, time passes measurably slower than in regions of weaker gravity. This effect creates remarkable phenomena at the event horizons of black holes, where time dilation becomes infinite relative to distant observers, effectively freezing objects at the horizon from an outside perspective. Gravitational time dilation also affects light traveling through space, causing gravitational redshift as photons lose energy climbing out of gravitational wells. This effect must be carefully accounted for when interpreting spectra from dense astronomical objects, as it can significantly shift observed wavelengths independently of cosmic expansion or Doppler effects. One of the most compelling recent confirmations of cosmic time dilation comes from observations of distant quasars, extraordinarily luminous active galactic nuclei powered by supermassive black holes. In 2023, astronomers Geraint Lewis and Brendan Brewer published groundbreaking research in Nature Astronomy, analyzing a sample of 190 quasars monitored over 2 decades in multiple wavebands. Their findings revealed that quasars located approximately 12 billion light-years away exhibited time dilation consistent with relativistic predictions, with time appearing to flow 5 times slower compared to our local reference frame. This measurement provides striking evidence for cosmic time dilation in the early universe, just over 1 billion years after the Big Bang. What makes this discovery particularly significant is that it resolved a long-standing contradiction in observational cosmology. Previous studies, including research published in 2010, had puzzlingly failed to detect the expected time dilation in quasar light variations. This absence of time dilation in quasars had mystified astronomers, with some suggesting exotic explanations, such as light bending by intervening black holes. The new observations effectively put these alternative theories to rest, confirming that quasars do indeed follow the expected relativistic time dilation, thereby strengthening confidence in standard cosmological models. Before the confirmation in quasars, one of the clearest demonstrations of cosmic time dilation came from observations of distant supernovae. When astronomers observe supernovae explosions across different cosmic distances, they find that more distant supernova appear to fade more slowly than their nearby counterparts. This aligns perfectly with relativity's predictions. The light from distant explosions undergoes time dilation due to the expansion of space during its multi-billion-year journey to Earth. Supernova time dilation has been consistently observed in explosions occurring 6 to 7 billion years ago, providing robust evidence for relativistic cosmology. The light curves of these distant supernovae, which plot their brightness over time, stretch in a precisely predictable manner based on their redshift, confirming that cosmic time dilation scales with the expansion of the universe. The famous twin paradox thought experiment illustrates time dilation in a way that relates to potential future astronomical explorations. In this scenario, one twin remains on Earth, while the other travels on a high-speed rocket ship and later returns. According to Relativity, the traveling twin experiences less elapsed time and ages less than the Earthbound twin. While human interstellar travel remains beyond our current capabilities, this effect would become significant in any future deep space missions approaching relativistic speeds. The twin paradox has particular relevance for understanding how time would be experienced differently by astronauts on long-duration space journeys compared to mission controllers on Earth, presenting both philosophical and practical challenges for potential interstellar exploration. Cosmic time dilation is intimately connected with the expansion of the universe. As space itself expands, light waves traveling through it become stretched, creating the cosmological redshift that astronomers observe in distant galaxies. This expansion affects not just the wavelength of light, but also the apparent rate at which distant events unfold. Lewis described the phenomenon succinctly. Looking back to a time when the universe was just over 1 billion years old, we see time appearing to flow 5 times slower. This occurs because as space expands, the interval between light pulses from distant sources also lengthens, making processes appear to unfold in slow motion from our perspective. The relationship between redshift and time dilation follows a predictable pattern. The more redshifted an object is, indicating greater distance and earlier cosmic time, the more pronounced the time dilation effect should be. This relationship provides a powerful tool for testing cosmological models. The fact that both supernovae and now quasars show this expected relationship offers strong support for the standard cosmological model based on general relativity and universal expansion. It counters alternative theories that had been proposed to explain the earlier apparent lack of quasar time dilation, reinforcing our understanding of cosmic evolution. The confirmation of time dilation in both supernovae and quasars has significant implications for cosmological models. Lewis described the findings as putting to bed some of the more extreme ideas that had been proposed, including that cosmologists have it all wrong, due to the previous failure to see quasar time dilation. This validation helps constrain alternative theories and solidifies the standard cosmological framework. Moreover, these observations provide additional evidence that quasars are indeed at the cosmological distances indicated by their redshifts, rather than being more nearby objects whose redshifts arise from some other mechanism, a hypothesis that some had proposed to explain the earlier lack of observed time dilation. Time dilation observations also help refine our understanding of the universe's expansion history. By measuring precisely how time dilation scales with redshift across different types of astronomical objects, cosmologists can test whether the universe's expansion has remained consistent with theoretical predictions throughout cosmic history. Any deviations could potentially indicate new physics beyond the standard model, making time dilation measurements a valuable probe of fundamental cosmology. Quasars serve as ideal cosmic clocks for measuring time dilation due to their unique characteristics. These extraordinarily luminous objects are powered by supermassive black holes actively consuming surrounding matter, creating accretion disks that emit tremendous amounts of energy. Because the accretion disks are relatively small, fluctuations in the light emitted by quasars can occur over timescales of just days, making these variations easier to track than slower astronomical processes. By monitoring these brightness fluctuations over decades, astronomers can effectively use quasars as ticking clocks from the early universe. In their groundbreaking study, Lewis and Brewer analyzed 190 high redshift quasars observed over 20 years by multiple surveys, including the Sloan Digital Sky Survey, Pan-STARRS, and the Dark Energy Survey. They specifically looked for patterns in the light variations across different wavelengths, green, red, and infrared, comparing how rapidly these variations occurred in quasars at different distances. Through rigorous Bayesian statistical analysis, they identified the signature of cosmic time dilation, finding that the variability timescales stretched precisely as predicted by relativity based on the quasar's redshifts. Detecting time dilation in astronomical observations presents numerous technical challenges. One significant difficulty is distinguishing between time dilation effects and intrinsic variations in the behavior of distant objects. For instance, quasars at different cosmic epochs might have inherently different variability patterns due to evolutionary changes in black hole physics or their surrounding environments. Researchers must carefully control for such potential differences to isolate the pure time dilation signal. Another challenge involves gathering sufficient long-term data. Time dilation studies require monitoring astronomical objects over extended periods, often decades, to accumulate enough variability information for statistically robust analysis. This necessitates consistent observational campaigns across multiple observatories and instruments with careful calibration to ensure comparable measurements over time. Additionally, researchers must account for various observational effects, including the Doppler shift, light travel time variations, and potential gravitational lensing, all of which can complicate the interpretation of apparent time dilation signals. Time dilation has practical implications that extend beyond theoretical astronomy to everyday technologies, most notably in global positioning systems. GPS. GPS satellites orbit Earth at speeds of approximately 14,000 kilometers per hour and at altitudes around 20,000 kilometers. At these speeds and elevations, both special and general relativistic effects become significant enough to affect timing precision. Due to their velocity, the satellites experience time dilation that makes their clocks run slightly slower relative to Earth-based clocks. Simultaneously, because they orbit in a weaker gravitational field than Earth's surface, they experience gravitational time dilation in the opposite direction, making their clocks run slightly faster. The net effect is that GPS satellite clocks advance faster than ground-based clocks by about 38 microseconds per day. While this might seem insignificant, without correction, GPS position calculations would accumulate errors of approximately 2 kilometers per day, rendering the system useless for navigation. GPS satellites therefore incorporate relativistic corrections in their timekeeping algorithms, making them one of the most common practical applications of Einstein's theories. This real-world implementation of relativistic principles provides daily confirmation of time dilation effects in a context that impacts billions of people through navigation systems. Time dilation also has significant implications for future space exploration, particularly for missions involving high velocities or strong gravitational fields. For long-duration missions traveling at significant fractions of light speed, as might eventually be developed for interstellar exploration, the crew would experience substantially less elapsed time than mission controllers on Earth. This time difference would create unique challenges for communication, mission planning, and the psychological well-being of astronauts who might return to find Earth much further in the future than their subjective experience would suggest. For missions near massive objects like black holes or neutron stars, gravitational time dilation would significantly affect operations. The movie Interstellar dramatically illustrated this concept with a planet where each hour of surface exploration equated to 7 years on Earth, due to proximity to a supermassive black hole. While this example is extreme, even modest gravitational time dilation would need to be accounted for in mission planning near massive objects. These relativistic effects add layers of complexity to the already challenging endeavor of space exploration beyond our solar system. One of the most intriguing controversies in observational cosmology involved the apparent absence of time dilation in quasar observations prior to the 2023 study. In 2010, astronomer Mike Hawkins published research examining nearly 900 quasars over periods up to 28 years, finding that quasars located 6 billion light-years away and those 10 billion light-years distant showed identical light variation patterns, with no evidence of the expected time dilation. This puzzling result contradicted both theoretical expectations and observations of supernovae, which clearly demonstrated time dilation effects. Several explanations were proposed for this anomaly. Some suggested that quasars might not actually be at cosmological distances, but could instead be more local phenomena with redshifts caused by some other mechanism. Others proposed more exotic possibilities, such as light from quasars being bent by intervening black holes scattered throughout the universe. Some even suggested that the finding might challenge fundamental aspects of the standard cosmological model. The 2023 detection of quasar time dilation by Lewis and Brewer has largely resolved this controversy, confirming that quasars do exhibit the expected relativistic effects and strengthening confidence in conventional cosmological interpretation of their distances and nature. Before the conclusive 2023 study, the absence of observed time dilation in quasars prompted consideration of alternative theories. Some researchers suggested that intrinsic evolutionary effects in quasars might counteract cosmic time dilation, creating an apparent cancellation that masks the expected signal. Others proposed modifications to standard cosmological models, including challenges to the conventional understanding of redshift as primarily indicating cosmic expansion. An interesting alternative explanation came from the theory of absolute Lorentz transformation, which suggested that time dilation might be directional rather than reciprocal. According to this perspective, only moving objects would experience time dilation, contrasting with the conventional relativistic view that time dilation effects are reciprocal between reference frames. While such alternative theories have now been largely superseded by the confirmation of standard relativistic time dilation in quasars, they illustrate the scientific process whereby anomalous observations stimulate theoretical innovation and more rigorous observational tests. Future research on cosmic time dilation will likely focus on extending observations to even higher redshifts, potentially observing time dilation effects in the earliest luminous objects formed after the Big Bang. Next-generation telescopes like the James Webb Space Telescope and planned extremely large ground-based observatories will enable detection of fainter, more distant objects with greater precision. These instruments will allow astronomers to track variability in objects from when the universe was just a few 100 million years old, providing new tests of time dilation in the very early universe. Additionally, improvements in statistical methods and longer observational baselines will enhance the precision of time dilation measurements. By monitoring known quasars and other variable objects over additional decades, astronomers can build increasingly detailed models of how time dilation scales with cosmic distance. This may reveal subtle deviations from theoretical predictions that could point to new physics or refinements in our understanding of cosmic expansion. Time dilation measurements offer a unique probe of cosmological parameters that complements other techniques. Because time dilation effects depend on the expansion history of the universe, precise measurements can help constrain models of dark energy, the mysterious force accelerating cosmic expansion. By comparing time dilation across different epochs of cosmic history, astronomers may detect subtle changes in the expansion rate that could illuminate the nature of dark energy. Furthermore, time dilation studies can help distinguish between competing cosmological models. For example, in theories that propose alternatives to dark energy, the relationship between redshift and time dilation might differ from predictions of the standard lambda CDM model. As measurement precision improves, time dilation observations will join other cosmological probes in testing fundamental aspects of our cosmic understanding, potentially revealing new insights into the universe's structure and evolution. Time dilation stands as one of the most profound and well-verified predictions of Einstein's theories of relativity, fundamentally changing our understanding of time as an absolute universal quantity. In the astronomical context, time dilation manifests dramatically across cosmic scales, with recent observations of quasars confirming that we perceive the early universe in slow motion relative to our local cosmic neighborhood. The 2023 detection of time dilation in distant quasars resolved a long-standing observational puzzle and provided further validation of standard cosmological models based on general relativity. Beyond its theoretical significance, time dilation has practical implications for technologies like GPS and presents both challenges and opportunities for future space exploration. As astronomical instruments and techniques continue to advance, time dilation measurements will provide increasingly precise tests of fundamental physics and cosmology, potentially revealing new insights into the nature of space, time, and the evolution of our expanding universe. Einstein's revolutionary insight that time itself is relative, not absolute, continues to shape our deepest understanding of the cosmos more than a century after it was first proposed.